Logarithms are something that always creates consternation and concern for students because it seems so foreign to us to have a mathematical operation described by a word instead of by some sort of symbol. But if we really think about it, many of the symbols that we use are very arbitrary, and it's only through experience that we get familiar with them. So for example, for a long time in our lives, we know that a little x in between two numbers means that we're supposed to multiply those. But then later, we see a slightly bigger x next to that same number, and we know that that means it's a variable. So then we change from 2x3, meaning multiplication, to 2 with a dot next to it, indicating multiplication. Or we have 2, and then we could have a set of parentheses surrounding one of the numbers, or both of the numbers, or just the first number, all indicating multiplication. And then, of course, if we have the 2 next to a 3 without any parentheses, but with a superscript or like this, then that indicates that it's not 2 times 3, but it's 2 times 2 times 2. Never mind the idea of this meaning division as well as this meaning division or this meaning division. My point being that we know all of these things and what they mean because we have experience with them. With logarithms, we just don't. And so at first there's a lot of discomfort with the idea of having a word meaning some sort of operation. So what we really need to do is we need to find a workaround. We have to find a way to help our brain understand what a logarithm is. And the statement that I want us to keep on going back to over and over and over again is this idea that a logarithm is an exponent. That's what it is. And if we go back up here to the start of our notes, what we have is an exponential function. Its inverse is a logarithmic function. So just like division is the inverse of multiplication, or subtraction is the inverse of addition, square root undoes a x squared, cube root undoes a cube. So we have all these inverse operations that we're familiar with. Well, a logarithm is an inverse of an exponent. And so what inverse functions do is they flip the inputs and outputs. So what I have to start off with is just a basic exponential expression that we're pretty comfortable with, where x is my input variable, and then I generate some sort of output y. Well, I can take those same three numbers, whatever the base of my exponential is, whatever my exponent x is, and whatever my output y is, and I can write them in logarithmic form, which just means my inputs and outputs are going to be reversed. So y is now going to be my input variable, and x is now going to be my output variable. And so then the base b of my exponential is the base b of my logarithm. So the best thing that you can do for yourself is to memorize post-haste how to get from exponential form into logarithmic form for all the same numbers, and vice versa. Take a logarithm and rewrite it as an exponential. And if you'll notice, the x that's here in this exponential expression is what the logarithm equals. That's what I mean by a logarithm is an exponent. So our logarithm, log base b of y up above, equals x. Well, x is the exponent in the companion exponential statement. So the first thing that we're going to do here in our notes is to rewrite these expressions from exponential form into logarithms, and then from logarithms into exponentials. So, for example, right here we have 5 to the third equals 125. We know that to be true. So what would that look like in logarithmic form? Well, my base b is the 5. My x in my statement, my exponent is 3, and then my y is 125. So I'm just going to take those three elements and I'm going to place them in my logarithmic statement. So log base b, so my base is 5 for the exponential, so that's going to be the base of my logarithm, so that's a subscript there. My y, my output of my exponential, becomes the input into my logarithm, so that's going to be 125, and then that equals my exponent, because again, a logarithm is an exponent, so that equals 3. In the second example, we'll do the same thing. So my base is 1/9. That's my b. My exponent is -2. And then my output y of this original statement is 81. So to rewrite this in logarithmic form, I'm going to have log base b. So my base is 1/9. My input into my logarithm is the output of my exponential. So that's my y, so my 81. And then that equals the exponent, because a logarithm is an exponent, -2. So there's the equivalent logarithmic statement of that exponential statement. And so then in the next section here, we're just going the opposite direction. So if we again think of this as being my base, this is my y, and this is my x of my exponential statement, just going back up to that top pattern. So we've got 2 as the base to an exponent of 4 equals 16. So there's our companion exponential statement for that logarithm, and then following the same pattern on the next one. So again, here's my base, here's the y, here's the x to parallel with the statement that we have up above. So my base b this time is 4 to the exponent -3 equals 1/64. And indeed that's the case. If we have 4 to the -3rd, that's 1 over 4 to the 3rd, and so 4 times 4 times 4 equals 64. So again, the sooner we get comfortable with being able to rewrite exponentials as logarithms and logarithms as exponentials, that will help us as we become more and more familiar with the concept of a logarithm being the inverse of an exponential. Now, to evaluate a logarithmic expression like the ones that we see in front of us, because we're still new to the idea of a logarithm, it's in our interest to try to rewrite these as exponentials and see if we can approach them that way. So for example, if I want to find what is the log base 3 of 243, what I'm going to do is I'm going to say, okay, let's let that equal a, or some variable. And so that gives me a structure to where I can now rewrite it as an exponential. So remember, using the pattern that we have above in our notes, the base of the log becomes the base of our exponential. So 3 is our base. A logarithm is an exponent, so a here is going to be my exponent, and then that's going to equal the input there, 243. And so hopefully we recognize that 243 is a power of 3. 3 times 3 is 9, times 3 again is 27, times 3 again is 81, times 3 a fifth time is 243. So that means that a equals 5. So that means that log base 3 of 243 equals 5. So the exponent that you would have to raise 3 to make 243 is 5. So log base 3 of 243 is 5. If we take the same approach on the next one, so again, set this equal to some variable. So let's say we go with u this time. Doesn't matter what. So we need to rewrite this in exponent form. Now you'll notice on this one, there's no base listed for us in our expression. So if we jump down the page here, there are 2 very common bases for logarithmic expressions. So we have the common logarithm, which is log base 10. So whenever you see log of something and there's no subscript there, there's no base, that means the default is base 10. So this implies here that it's really log base 10 of 1 over 100 equals u. So the default is base 10 if there's no base listed. And then we have this other base, if you recall from our exponential notes, we have this natural base e for some expressions. So that is also commonly used in logarithms. And so if we see, if we have a log base e that we want to use, we don't write log base e. Instead, we use this ln to represent that it's the log base e. So we would never write log base 10. We would just write log. We would never write log base e. We would just write ln. And so on your calculator, there are 2 buttons, a log button and a ln button. And so the log button is the default base 10, and then the ln is the natural log, so log with a base e. But to go back to our example here, so once we recognize that it's base 10 when it's not listed there, now we can go ahead and rewrite this as an exponential in a more familiar format for us. So we can say 10 to the u power equals 1 over 100. So remember, 10 is the base of our logarithms, that's the base of our exponential. U is the exponent, so whatever a logarithm equals, a logarithm is an exponent, so that's why u goes to the exponent, and then equals the input to the logarithm, so that becomes the output of the exponential, 1 over 100. Well, what does u need to be to equal 1 over 100? Well, hopefully we can see that it's got to be -2, so that means log of 1 over 100 equals -2. So for the last one of the set, we again are going to set this equal to just some variable, doesn't matter what, so we can say c this time. So now I want to rewrite this in exponent form. So it's going to be my base of my logarithm becomes the base of my exponential. Logarithm is an exponent, so 1/2 to the c power is going to equal 32. The input of my logarithm becomes the output of my exponential. So hopefully we recognize 32 as being a power of 2. So 2 times 2 is 4, times 2 again is 8, times 2 a fourth time is 16, times 2 a fifth time is 32. So now I have to figure out, all right, what do I need to make c equal so that I'll have these two sides equal to each other? Well, the first thing I'm going to need to recognize is that c needs to be negative, because that will then flip the fraction that I have if we think to our exponent rules. And then if we do that, so now, what we can do is we can say 1/2, make that 2 to the -1st to the c power equals 2 to the 5th. So now the question is, what does c have to be so that these two sides will be equal to each other? Well, when I raise a power to a power, I'm going to multiply, so that means for these two sides to be identical, c is going to have to be -5. Or in other words, log base 1/2 of 32 equals -5. So again, we don't have a lot of experience with logarithms, so what can we do to help us understand them better? Rewrite them as exponentials, and the way we rewrite them as exponentials is to go back to this statement here that's all doctored up now and make sure that we, as soon as possible, commit to memory this process of how we rewrite an exponential expression in a logarithm. How do we rewrite a logarithm as an exponential?